Hi everyone. Today we're going to take a look at the factor theorem, and the factor theorem is kind of a big deal in algebra. So the idea behind the factor theorem is this is a link between all of the stuff that you've done with factoring and some properties of these polynomial functions if we look at them on a graph. So we're going to start out with this first example, y equals x cubed plus 2x squared minus 8x, and you'll notice the first question just says factor this polynomial. That should be easy for you at this point. That should be something that you've done lots of times. So if I was going to start to factor this, the very first thing I would look for, as always, is a GCF. And it looks like I can pull an 8, or I'm sorry, not an 8, an x out of everything. So I'm going to start by taking out an x, and I would be left with x squared plus 2x minus 8. But then, as always, we want to see if there's any further we can go. We want to look at this polynomial here and ask ourselves if this can be factored further. Well, this is a trinomial, and so I'm pretty sure, as long as I can find the right pair of numbers, pretty sure I can factor it this way. I'm trying to multiply to make a -8, so I know I'm going to have to use one positive and one negative number. And I need numbers that multiply to -8 but add to +2. So if I use a 4 and a 2, that should work for me. I just want to set them up so that this 2 comes out to be positive. So I'm going to do a +4 and a -2, and then also bring down my GCF of x. So this is what this polynomial would look like in its factored form. Okay, so now the next question, which is a seemingly unrelated question, wants me to graph that polynomial and take a look at it on a graph and look at the zeros. The zeros, by the way, that's another word for roots. Okay, and then it wants us to look at what the relationship is between the factors and the zeros of the function. So let's take a look at this graph on Desmos real quick. So we found when we looked at Desmos that our zeros, or our roots of the function, were located at x equals 0, x equals -4, and x equals +2. And so look at those three numbers compared to your factors, okay? You should notice they're related. They're not exactly the same as what you see. For example, I see a -2 here, but this is really just a regular 2. However, in algebra, you're pretty used to that. That kind of stuff happens all the time. And here's why that happens the way it does. When I'm trying to find the zeros, the reason those points are called the zeros is it's the places where the function is equivalent to 0. So really this is what I'm doing, is I'm setting this thing equal to 0. Well, if any one of these things, any one of these factors was a 0, then you'd be multiplying by 0 and the whole thing would come out being equal to 0. That's something called the zero product property. So let's jot that down real quick here. The zero product property . And this is review. You've learned this property before. Typically, we talk about it in Algebra 1. I'm not sure if you guys saw it last year in Algebra 1, but you've definitely learned about it before. Zero product property basically says if something times something is equal to 0, if I know two things multiply to make 0, one of those things has to be a 0. So then either A equals 0, A equals 0, or B equals 0. So if you think about that compared to what we just wrote down, we factored this thing. So this is a product, right? It's multiplication. And if I know this times this times this is equal to 0, then this could be a 0, or x plus 4 could be equal to 0, or x minus 2 could be equal to 0. So x could equal 0, or x plus 4 could equal 0. Which, if that were the case, if x plus 4 were equal to 0, doesn't it make sense that x would be -4? And then x minus 2 were equal to 0 would give us x equals 2 as a root. Okay, so what is the relationship between the factors and the zeros? We kind of just talked about that each factor, if we set the factors equal to 0, and solve, what we end up with is the roots or the zeros of the function. And like I said, that is a really big deal in algebra. Okay, so that's what the factor theorem really says for us. Factor theorem says that C, and we're just using C to represent some number, C is a zero of a polynomial function, and remember zero and root are the same thing, just so you know when I use those words kind of interchangeably. If and only if x minus C is a factor of f of x. Okay, so the relationship between roots and factors is the big deal today. Okay, what you're going to see me write this down in class as is if some number is a root, then x minus that number is a zero. I should have, sorry. This is what happens when I try to write this while I'm talking. If a number is a root, then this factor is a factor of the polynomial. And this goes both ways. So if I know a factor, then I can find a root. And if I know a root, then I can find a factor. Okay, so knowing both of those things and both of those relationships is going to be really important. So for example, if you look at example 2, I'm giving you this big ugly polynomial and I'm saying to factor it. And we have all these factoring tricks up our sleeve, right? We could factor by grouping. This isn't a trinomial, so I know that's not going to work. There's no GCF here. I mentioned grouping just a second ago, but I actually don't think grouping is going to get us very far. I mean, I could pull an X out of these first two, but I don't know if I can get much further than that. So we're kind of stuck. We're kind of stuck on this one. We're not going to get very far with using our typical factoring methods, and I think you'll see why in just a second. So here's what I'm going to do is I'm going to say, okay, I can't find the factors. Can I find the roots? So I'm going to take this function, I'm going to graph it. And again, I'm going to head over to Desmos here in just a second, and we'll graph this function, and we're going to find the roots, and then once we've done that, then we can turn those roots into the factors. Looking at in example 1 is x cubed plus 2x squared minus 8x. Okay, we'll zoom this out because I feel like we're not seeing the whole thing. There we go. Okay, and so the question was, where are the zeros of this function? Zeros, by the way, are the same things as roots, which are the same things as x-intercepts. I'm looking for the places where this thing crosses the x-axis. So Desmos is really nice for that. It shows you right where they're located. You can just click here, and I see that I have one root at -4, one root at 0, and one root at 2. Okay, so the answer to that next question, and we're going to write it down on our paper in just a minute, is we have zeros at 0, -4, and 2. And now what I want to do is look back at our factored version, which, by the way, the factored version looked like this. X times x plus 4 times x minus 2. And I just want you to see that that's the exact same function. Okay, so this is just a rewritten version of the function up above. Okay, they're exactly the same. But I want you to look at the relationship between these factors and the three roots that we just located. I went ahead here and typed in that polynomial from our example 2 into Desmos, and from this graph I can see where the zeros are located. So I have a 0 located at -1.5, and I'm jotting these down on my paper and I'll show you that in just a second. I have a 0 located at 0.6 repeating, which your life is going to be a lot easier if you can recognize that as 2/3. And the last one here would be x equals 5. So I have found my 3 zeros. And now what I can do is I can take those 3 zeros, or those 3 roots, and turn them back into factors. Okay, so let me show you that real quick. Oops. There's our notes. I'll make that big for you guys. All right, well, we'll just deal with it like that. Okay, so I've got my 3 zeros, right? I've got the -1.5, I've got the 2/3 and the 5. And so what I know now is that any number that's a root can be turned into a factor by just writing it as x minus that number. Now, here's the problem. When we factor using integers. You've never seen us write factors with fractions or decimals in them, okay? And you won't, because the idea of factoring is to use whole numbers, okay? So this is the problem that we're running into, is I could write x minus 2/3 as a factor, but that's not factoring using integers, okay? So what I'm going to do instead is I want to somehow write a factor where if I were to set it equal to 0, the x would come out equal to 2/3. Okay, so let's think about what would have to happen here. The first thing that I would do if I was solving something like this, and really here's what I want you to imagine. There's a number here in front of x, and there's, I don't know, a number being added here, and that might actually be a subtraction, but we'll get to that in just a minute. Okay, and I want this answer to come out to be 2/3. So if I'm solving something like this equal to 0, the first thing I'm going to do is slide this number over here to the right side, and then I'm going to divide by this number here. Okay. By the way, what I'm about to show you is going to become a pretty quick shortcut for you, but I'm kind of just trying to explain why this is a shortcut. So if I want my answer to come out to be 2/3, the first number that I want to land over here is this 2. Okay. Which means what I really want in this spot here is a -2. Because if I put a -2 there, and I move it to the other side, then I would have like an equals 2 on this side. And then I would divide by whatever's number is in front of the x here. Well, if I make that a 3, then if I were to solve this thing, I add the 2 to the other side. And I divide by the 3. And voila, I end up with x equals 2/3 as a root. So all of those scribbles, and I'm sorry I just made a mess of our paper here, but is to tell us that if we want the factor x minus 2/3, I'm going to rewrite that because I wish I wouldn't have scribbled it out now. If I want this factor x equals 2/3, but I want it using integers, I can just take this denominator and slide it over here in front of the x, okay, and make it a 3x minus 2. So again, if you didn't follow what I was doing here, think to yourself, if I had 3x minus 2 equal to 0 and I solved that, does it make sense to you that 2/3 would come out as the answer? Because I would move the 2 to the right and then I would divide by the 3 and I would have my 2/3. So let's think about this one. And I'm going to take this -1.5 and I'm going to write it as a decimal, or I'm sorry, as a fraction. So that -1.5 is -3/2. Which means that if I were to write it as a factor, it would be x minus -3/2. So if it's minus a negative, I'm really writing it as a plus 3/2. And so just like I kind of talked about here, what I'm going to do is I'm going to take this 2 and just put it as a coefficient on the x. So I'm going to make it 2x plus 3. And again, the reason I'm doing that is if I had 2x plus 3 equal to 0, and I slid this over, I would subtract 3 and then divide by 2, and I would be left with -3/2 as my root. This one's the easiest one. I probably should have started with this one. If it's just x equals 5, your factor is x minus 5. And so this thing right here is a factored version of my original polynomial. So I did that by finding the roots first and then working backwards and finding the factors, which, by the way, so now when I hand you a problem like this and I ask you to factor it, you could just graph this thing and find the 3 zeros. You could find these first and then turn each one of them into factors. So this would be like x minus 0, which is the same as just x. This would be x minus -4, otherwise known as x plus 4, and this would become x minus 2. Okay, before we go any farther, I want to tackle the concept of synthetic division. So synthetic division is meant to be a shortcut for long division, for polynomial long division. And it only works in certain circumstances, and I'll show you that in just a minute. But what it's really helpful for is situations where you've got some big, ugly polynomial that you really don't want to work with in terms of factoring or graphing even. And you know at least one of the roots or one of the factors. If you know one of the roots or one of the factors, what you can do is you can divide it out to find what the other factors are. Okay, so that's what synthetic division is meant to help you do. Okay, so let's suppose I give you this polynomial. And I did just add this in here, so you'll want to jot this down on your paper. But let's suppose I give you this polynomial, and I'm asking you to either factor it or find the roots. This could work for either one of those questions. And so if I look at this thing and try to factor it right now, I'm not going to get very far. This is another situation where grouping isn't really going to work. It doesn't fit any of my other types of factoring. But I know this. I'm given one of the roots, and now my goal is to find the others. Okay? So I can do something called synthetic division to kind of divide this root out of there. Here's what synthetic division is really doing. If I know that 3 is a root, then I also know that x minus 3 is a factor. So this is essentially me taking this polynomial and dividing by x minus 3. I could do long division if I wanted to, but synthetic division is meant to be a shortcut, okay? So what I'm going to do is I'm going to start with the root number. Now this is important for synthetic division, that you're using the actual root, not what you're seeing up here. See how this is negative up here? Remember that your factors are always x minus the root number. So you always have to pull this number out like as the opposite of what you're seeing it in the factor. So I'm going to take that 3 and I'm going to put it here. And then I'm going to take my coefficients off of this polynomial and I'm going to lay them out horizontally. So I'm going to go 2, -1, -13, and -6. Which mean, remember when we did long division and I made a big deal about how if you were missing a particular term in the sequence, you had to make sure to put a 0 in there? That same thing is going to hold true here. So if I was like missing an x squared term, I would make sure to put a 0 here. Okay, just keep that in mind. Okay, and then I'm going to leave like a line of blank space and draw a line here. This first number drops down as a 2. And then what I'm doing is I'm taking this 3 and multiplying it by the 2, and I'm getting a 6. And then I'm adding these together. So -1 plus 6 is 5, and now I'm repeating the process. I'm going 3 times 5 is 15, and then I'm adding these together. So -13 plus 15 is +2. Now I'm going 3 times 2 is 6, and -6 plus 6 is 0. I like that this is 0 because this number that shows up on the end when you do synthetic division, this is your remainder. Okay, so in this case, because I knew that 3 was a root, so x minus 3 had to be a factor, this better come out with a remainder of 0. Because if something is a factor, that means it divides into it evenly. So let's talk about what the heck these numbers really mean. Is what I just did is I took this polynomial and divided by x minus 3. Which means that now what I should be looking at is a quadratic polynomial. I took one degree of x out, so my 2x cubed is now an x squared. So this gets an x squared on it, this gets an x, and then this number here doesn't get anything at all. This is the remaining polynomial, okay? So this is like the answer. If you were to do long division, if you were to take this thing and divide it by x minus 3 using long division, this is the answer you would get. The reason we like this now is if I'm trying to find roots, this thing is a quadratic, okay? So now we could use the quadratic formula to find my other 2 roots, and then if I could find the roots, I would be able to turn them into factors. Or I could probably even use my factoring methods now. I could say 2 times 2 is 4. So now I'm looking for numbers that multiply to 4 and add to 5. Here, I'm just going to write that I'm factoring here. So I would do 2x squared plus 4x plus 1x plus 2. So again, remember I'm using my old factoring methods that we already learned. 2 times 2 is 4, and I'm looking for numbers that multiply to 4 and add to 5. So I chose 4 and 1. Now I'm going to group. So I'm going to take out a 2x, and that leaves me with an x plus 2. Out of these 2, I can't really take anything except a 1. And that's going to leave me with an x plus 2. And then I know my factors are 2x plus 1 and x plus 2. And then don't forget that we also know that x minus 3 is a factor. So really I should, and I'm out of space here, but I should squeeze that in as well. So if I was trying to factor this polynomial and I knew one of the roots, this is how I could divide out that root, get down to the point where I'm looking at a quadratic, which gives me a trinomial, and now I know how to factor that thing. Or I could have done quadratic formula, found that my roots would be, let's see, this root would be -1/2 and this root would be -2. And I could have turned those things into factors that way. So synthetic division is supposed to be a shortcut for polynomial long division. Only really works when you're working with little factors like this. It wouldn't work if you had like an x squared that you were trying to divide out. You would still have to go with long division for that. Okay, but we'll be using synthetic division quite a bit. Again, the key to it is taking the root number and setting it here, lining up your coefficients across the top, and then bringing this number down and then multiply and add. Multiply, add, multiply, add. And then this number on the end is always your remainder. Here you always start 1 degree less than what your original polynomial was. Okay, let's try, I think you have one more example. So it says, write an equation for a polynomial function with these zeros. And notice this does not say your polynomial has to be in standard form, which is a saving grace here, that we're not going to have to do a whole lot of foiling, okay? If I know my zeros, remember every one of these zeros can turn into a factor. So if I have a 0 at -3, I know I have a factor at x plus 3. If I have a 0 at 0, I have a factor of just x, because that would be like x minus 0. And then remember, for 1/2, this would really be like x minus 1/2, but we don't ever leave fractions in our factors, so we're going to do that thing where we slide the 2 over, and we're really going to turn this thing into a 2x minus 1, because that would have a solution of 1/2 if you set it equal to 0. So my polynomial function in factored form would be x times x plus 3 times 2x minus 1. Whoops, that's supposed to be a minus. 2x minus 1. And again, this would give you a 0 of 0. This would give you a 0 at -3, and this would give you a 0 of 1/2. Okay, look at that next question. Write another equation for a polynomial that has the same zeros, but now I want it to have degree 4. I should point out here, this thing has degree 3, because if I did go through and multiply this all together, which is what I would have to do if it said in standard form. It did not say that here, so I can just leave my answer this way. But if it said standard form, I would have to go through and multiply it all out. I would somewhere in there end up with an x cubed, because I have an x times a 2x. So this polynomial function right now has a degree of 3. To make a degree 4, but without putting another like extra 0 in there, without making up a new factor, I'm going to make use of something called multiplicity. And multiplicity is a term that we're actually going to define later in this chapter. But really what that means is it's possible to have like 2 of the same factors and have them share a 0. So for example, if I had another factor of x plus 3 in here, it's like I have 2 copies of this factor. Both of them would give me a 0 at -3. So that means that this 0 has what's called a multiplicity of 2. Okay, if I had 2 copies of that factor. Now, the easy way to write that would be to write that factor as though it were being squared. So one of my options would be to say, I'm going to just say that I have 2 copies of this factor. This would give me an entirely different function, but the zeros would still be in the same place. Okay, and we're gonna look at the graph of this thing in just a minute, and I'm going to show you how that multiplicity works on the graph. Okay, you've actually seen this before, you just didn't know that's what it was called. I didn't have to do it to that factor. I could have put a square on this x here. I could have put a square on this one here. I just want an extra copy of one of these so that I'm not creating a new 0, but so that I have multiple copies of one of the zeros. Okay, let's look at this thing on a graph real quick. Last time, I'm going to go ahead and graph that original function that we came up with. So we said x times x plus 3 times 2x minus 1. And if you look at this polynomial, it's got zeros at -3, 0, and 0.5, which is 1/2. Okay, those are the three places we wanted our zeros to be. If I jump in here, whoops, you know what I'm going to do is I'm going to copy this. Okay, but now I'm going to take the x plus 3 and put a square on it. So look at that blue graph. The blue graph looks totally different, right? It's an entirely new polynomial, but it still has roots at -3, 0, and 1/2. If I turn this one off for just a second, look at that. Well, look at what happens at that -3, how that multiplicity works. We're going to talk a lot more in this chapter about the shapes of these graphs, but you'll notice that when a root has multiplicity, it's like the graph comes down and touches it, but it doesn't go all the way through the axis. It turns around and runs back the other way. That's how you can tell from looking at a graph that a zero has multiplicity, okay, that there's more than one of them. Let's look at what happens if instead of that, I square this one. Okay, so once again, here at the 1/2, you'll notice that the graph kind of bounces down, it hits that 1/2, and then turns around and runs the other way. And that's how I know that I have duplicate copies of that 0. Okay, or I could square that x. And you'll notice that again, the graph touches at 0, but it doesn't go all the way through. Okay, that's a duplicate 0. That's a multiple 0. Okay, that's called having multiplicity. If I wanted to, I mean, we could have a lot of fun here. We could square all of them. Make a really crazy looking graph, but you'll notice the graph bounces off of all three of those points. Now, that wouldn't answer our last question because the last question wanted a degree of 4, and this would actually have a degree of 6 because I would have an x squared times an x squared times another x squared. Okay, so this would be a degree 6 polynomial, not a degree 4. But that's kind of the idea with multiple roots. Okay. The other thing I should probably point out while talking about these functions, and actually let me just do this. Let me go back to our original here. The other way you can change a polynomial and make it a whole new graph without changing where the zeros are located is you can put a leading coefficient in here. So if I put like a 5, let's say, in front of that x, that's going to do a transformation on my function, but notice it doesn't change where the zeros are located. So that green function is a whole new function, but it still has the same zeros as the original. Okay, or I could put a negative in front of it, and that's going to flip everything over. Now I've got a whole new function, but the zeros are still located in the same place. Okay, so all just important things for us to understand about how these zeros work with the factors and how to build these polynomial functions.